It is at the core of human ambition to explore and search for things that have never been seen by human eyes. While many consider space to be the final frontier, our planet's vast oceans hold a wealth of discoveries yet to be made. To facilitate research in this harsh environment, engineers have been tasked with designing submarine dwellings for scientists to live and conduct experiments for extended periods of time. One large hurdle that must be faced is geotechnical issues in the submerged environment. This presentation will look at recent developments and research being done to make these submarine dwellings more feasible. Soil friction is one of the most important factors in the bearing capacity of a soil. This can be clearly seen in the famous Terzaghi equation, where cohesion of soil and the friction angle play such a major role in determining the bearing capacity of a soil. Complications begin to arise when looking at the soil friction in a submerged environment. This is because the soil friction is highly variable and the cohesion does not necessarily have a linear relationship to time. Studies have shown that in cases regarding soils with a high silt content, the cohesion was increased when the soil was saturated. The soils that had a high clay content behaved differently though, with a decrease in cohesion when the soil is saturated. In bridge structures crossing rivers or other moving water bodies, the smaller soil particles are often swept away by the moving current, which leaves sands as the primary soil type that is being designed for. When looking at submarine building possibilities, the soil properties become much more variable. This is due to the fact that the submarine structures have the possibility of being constructed for the most part on any area of the coastal sea floor. This means that the soils will not be quite as consistent as they are beneath bridges. Soil friction is reliant on water content, but it is also reliant on the makeup of a soil sample. Taking soil samples underwater is full of inherent sources of error and difficulty. The process of taking boring logs and performing in situ testing are also more expensive underwater than on land. Another major issue with an underwater structure is that there are a significantly larger number of lateral loads that the structure and foundation must face. These can come from a variety of sources, but one of the major ones is the constant water movement. Water has a larger unit weight than air, which means that it will impart a larger force than air would on an above-ground structure. To accommodate these forces, the foundation must be specifically made either deeper or much wider than it would need to be on land for the same structure. While there are not many undersea habitats, there are a small number that already exist. By looking at these, more issues surrounding the construction and foundations can be uncovered. Understanding these hurdles can help decrease costs and risk in the future. The first underwater dwelling to have people live in it was the Conshelf 1. It was built in 1962 under the guidance of the famous ocean explorer Jacques Cousteau. This structure was very temporary and only used as a proof of concept for Conshelf 2. This structure was much larger than the first, but it did not use a solid foundation. Instead, it was supported by legs with large metal plates at the bottom. The plates act as a sort of artificial footing for the structure. In this case, the large metal plates are not formally rooted in the soil. This means that they are more prone to washout, but they are also able to adjust to these changes because they do not have a rigid connection, but rather a hinge. While this was ideal for the mission it was used for, this is not a long-term solution to the submarine foundations. The Hydrolab was a more permanent structure built in 1966 off the Bahamas. It was built by the National Oceanic and Atmospheric Administration as a research station to study sea life long term. In order to increase the life of the structure, it was built on a large concrete foundation. The habitat was attached to the foundation by 4 legs that were bolted into the concrete. This massively increased the structure's lifespan as it was not decommissioned until 1985. Due to the depth of the foundation slab, washout was not a major issue, and the small size of the structure meant that there was little to no differential settlement due to weight. The life of the hydrolab proved that a slab foundation can work for a small structure, but it wasn't until much later that research was done on the possibility of a larger one. Aquarius is a massive undersea research station off of Key Largo that has seen extensive use by various groups, including Florida International University. This structure is supported by massive steel legs on wide footings. Because of the scale of the building, maintenance is of utmost importance. Washout has been a significant problem with the Aquarius sea base. In order to combat this, divers have resorted to building a wall of sandbags into the soil around each footing. While this may seem as unorthodox, the same technique is used in slope stability as a support for dirt embankment. Sandbags are used above ground to create solid groupings that can resist lateral pressures of the soil much greater than loose dirt would. Even though there is no slope in this case, the goal is still to resist lateral movement of the soil. The fear is that washout would harm the structure rather than slope instability, but the concept remains the same. Under is a partially submerged restaurant currently being built in Norway. The main structure was built above ground and it was then lowered onto a continuous concrete foundation. With a structure this large, serious support is needed to keep it from facing settlement issues. Individual footings like those that have been mostly used before would not provide the necessary stability to hold the structure. The building is also helped by its massive footprint. In this case, the horizontal space was needed anyway to provide massive views of the ocean. It is wise to design the function of the building and the structure in tandem so that the two important aspects are working together. Even though underwater construction has been going on since the 1960s, the field still seems to grow ever slowly. Like space, the oceans can be a harsh and difficult place to put permanent structures. When looking at the history of submerged construction, the progress made in overcoming geotechnical hurdles becomes clear. It may not come today or tomorrow, but someday soon, long-term underwater construction will become a viable option for both scientific and recreational purposes.